it's a pleasure to be here in this prestigious place, you know. Institut Pasteur is such a wonderful place for this wonderful, experience. So, as you said, it's basic science, but what is absolutely fantastic in what I did is that for decades I was doing only basic science. But it turns out that by the end of my career, because I have to admit that I'm close to the end of my career, there are more and more applications of what I thought one was only basic science, and this is wonderful, the idea that what you have done may be useful. If you want to read something about not exactly what I have done, but what I have done is related into the thinking of Einstein. And so you have this small book with absolutely zero equation. This one is in French. This is the English version. You can buy the English version if you don't, if you are not fluent in French. And if you are fluent in Chinese, you can also have this version, which is in Chinese. Also in Italian, which is a quite exotic language. I'm testing if you follow or not. Okay. So, just rapidly, I want to put my finger on a popularization series, which is called Science Étonnante. You have dozens of excellent videos on explaining for general public many subjects, including biology, including mathematics, including some economics. And most of them have subtitles in English, so I highly recommend it. So, Science Étonnante, I recommend. Okay. So the starting point is that quantum physics is strange. It's not irrational, but it is strange. What is quantum physics? It's a mathematical formalism allowing one to perfectly describe facts that you observe and that you cannot describe in classical physics. I will come back to this later. Stability of matter, matter-light interaction, superconductivity, superfluidity, all that you cannot understand in the framework of classical physics. It's not only a mathematical formalism allowing you to understand what you have observed, but it also allows you to predict what will happen if you go to the lab and do this or that. For instance, entanglement was predicted in the theory. I went to the lab and I observed that entanglement was as extraordinary as predicted by the theory. Maybe this is a difference with economy, Jean, that in physics, when we predict something, usually we observe it. I'm teasing him, okay? Not only it allows you to predict basic phenomena that you observe in the lab, but it also allowed one to invent new devices not very important, like a transistor, integrated circuit, laser, etc. I will come back to this point. But the problem with quantum mechanics is that it cannot give you simple images to represent, or there are no simple images to represent the formalism in our world. You can do it mathematically, but not in our world. And so this is one of the reasons why it's so complicated. Okay. Well, I say no, do not draw no-nonsense consequences. This is a warning to journalists if there are some in the room. Okay. So beware wrong reasoning, like quantum physics is strange, bending spoons at a distance by mind is strange, so bending spoons at a distance is a quantum effect. You know, well, you find some kind of reasoning like that. Okay. So we have two quantum revolutions based on two concepts. The first quantum revolution is based on wave-particle duality, where the two big names are Einstein in 1909, wave-particle duality for light, and Louis de Broglie in 1923, wave-particle duality for matter. Second quantum revolution is based on entanglement, and the great names about entanglement are Einstein, Podolsky, and Rosen, Schrödinger, and John Bell 30 years later. Okay, let us start with the first quantum revolution in a nutshell, but I think it's not bad to think of it again. So quantization is the fact that some quantities which are considered continuous in classical physics, you have to describe it as made of discrete quantities. For instance, light, which is a wave, and you think of a wave of something flowing continuously. Einstein in 1905 say in some circumstances you have to consider light as made of grains of energy, elementary grains of energy, call them least quantum, and you need that to interpret a certain number of phenomena. But of course, Einstein knew of the wonderful work of Thomas Young and Augustin Fresnel in the beginning of 19th century, and of Maxwell later in the century, describing light as a wave and describing many phenomena. So how can it be both a wave and a particle? Well, Einstein wrote a wonderful text in 1909, which for the first time invoked duality. Light is both a wave and a particle. Wave-particle duality for matter, that's the reciprocal. We have particles, electrons. We think that electrons are particles, but in some circumstances, you have to think of them as waves. And it is Louis de Broglie who made that hypothesis in 1923. And this allows you to understand phenomena which are impossible to understand in classical physics. For instance, stability of matter. At the end of the 19th century, physicists knew that matter is made of positive and negative charges. And everybody knows that positive and negative charges attract each other. So how is it that matter doesn't collapse on itself? And the answer is quantum mechanics. Here is the best example. Rutherford atom model say that you have a nucleus, which is positive, and you have electrons, which are trajectories around the nucleus. It's just like satellites around the Earth, okay? But Niels Bohr discovered in 1913 that you have to impose conditions on these orbits. It's not any orbit which is possible, it's only certain precise orbits. And in 1923, Louis de Broglie understood where the Niels Bohr quantization condition comes from. It says, look, if you are on a trajectory like that, if you think that the electron is a wave, the wave has to come after a round trip as in phase with itself. In other words, the number of wavelengths must be an integer around a full trajectory. And this is enough to understand why you have to quantize the trajectories here. Okay. Okay, so what happens now? Okay, like that. So electrons, which are particles, are also a wave, and once again, wave-particle duality. I love this photo, don't you? Look how they are happy. So if you want to convince people that it is really fun to do quantum physics, you have to show this photo. Look, this is Louis de Broglie. Look, he looks a little bit like Groucho Marx, don't you think so? Okay. And Schrödinger is very happy also because he has just found the equation for describing matter waves. Okay, so it's one. I just flash something showing directly wave-particle duality for a single photon. It is an experiment which was done by my first PhD student, Philippe Grangier, a few years after my experiment in 1986. We have a source, and we claim that this source emits one photon at a time, really. One photon, then one photon, then one photon. And what happens if we send one photon on a beam splitter? Everybody understands what is a beam splitter. Like a piece of glass, if light comes on a beam splitter, a fraction of the beam is transmitted, a fraction of the beam is reflected. But if you really believe that you have a single particle, the single particle will not be split in two. So you are going to observe it either here or here. And to demonstrate it, we did an experiment in which we have an electronic circuit here, which is called the coincidence circuit, which is able to tell you if you have or you don't have joint detection. And we found no joint detection. This proves indeed that the photon goes either on one side or on the other side. But if we do this experiment, in which after the beam splitter, we recombine the two paths on another beam splitter, Everybody who has done a little bit of optics knows that this is an interferometer. That is, in terms of waves, you think that you have the wave arriving here, split in two, and recombined. And after a combination, the fact that you detect here or there depends on the path difference between the two paths. So if you move this mirror, then you are going to observe a modulation of what you observe here and a modulation of what you observe. And this is what we observed with the same source of single photon. So in that second experiment, the single photon behaves as a wave which is split in two and recombined. And I insist, it's the same source, the same beam splitter. Okay, this is wave-particle duality. So it's both a wave and a particle. Bohr, facing this strange phenomena, would have told us, look, it's not so extraordinary, because if you think about it, you cannot do the two experiments simultaneously. You have to choose either to ask the first question or to ask the second question. You cannot ask the two questions simultaneously, so there is no logical inconsistency. This is acceptable to a point, but anyway, it has to be known. Just to finish with the first quantum revolution, the first quantum revolution was first conceptual and scientific. Conceptual, I told you, the concept is wave-particle duality. Scientific, understanding the structure of matter, its stability, its interaction with light. I told you, understanding the stability of matter, you cannot understand it if you don't have quantum mechanics. It was technological. The laser, the transistor, and the integrated circuits were invented and are at the root of the society of information and communication. And at this point, it's a good time to tell you that it takes a long time between basic discoveries and application. Quantum mechanics emerged in the beginning of the 20th century. The formalism, well established, was established in 1925, and transistor was invented in 1947, laser 1960, integrated circuits 1970. So it takes decades between the original development of fundamental theory and the moment when people can apply it. Remember that. The second quantum revolution. The second quantum revolution is based on entanglement, and I'm going to show you what is entanglement, taking the example of two photons. And the reason why I take the example of two photons is because it is with two photons that most of the most convincing experiments have been done, including mine. So you have a first photon going to the left, second photon going to the right. They don't have the same color. It's not important. What is important is that we are going to measure the polarization. So you know, probably most of you know what is a polarization. When you have a light wave, the electric field vibrates perpendicular to the direction of propagation. That is, it is in a two-dimensional space. So you can describe it on a basis in a two-dimensional space, okay? And so you are, for instance, with axis X and axis Y. Now, when you quantize light, you obtain a quantum object, but it retains some properties of the wave where you started. So you quantize a wave of light wave, and then you have a photon. But the photon also has a polarization. So it can be polarized along X, or along Y, or along any intermediate position. Now here I have a polarizer. The polarizer has an axis A. If light is polarized along A, it gets out in channel +1. If it is polarized perpendicular to A, it goes out in channel -1. And if it is a classical light beam, if it is polarized in between, a fraction goes in +1 and a fraction goes in -1. But if you have a single photon, it's always the same story. It will go either to +1 or to -1. And so what you do, you repeat the experiment many times, and at the end you look for probabilities. And the quantum formalism allows you to calculate the probabilities for a given state. This is the Einstein-Podolsky-Rosen Bohm, because Bohm added his grain of salt, entangled state. And you are going to have an idea of what is extraordinary in entanglement. XX describes a pair of photons both polarized along X. Simple to understand. YY is a pair of photons both polarized along Y. No difficulty to understand. But the quantum formalism tells you if this is a valid state and that is a valid state, the superposition of the two is also a valid state. And that state, I cannot describe it by moving my hands. The reason is that people who know enough of mathematics will easily recognize that you cannot factorize it. You cannot put it in the form of the product of something for the first photon and something for the second photon. If you could do that, you could say the first photon is polarized like that and the other one polarized like that, but it is impossible. You have to accept the fact that the pair of photons is both this and that, and there is nothing to add. It's as surprising as the Schrödinger cat, which is both dead and alive. Of course, there are more particles in a cat, okay? It's not only 2 photons in a cat. But from a conceptual point of view, it's as surprising. This is why entanglement is so extraordinary. So as I told you, the quantum formalism allows you to calculate the probability, and the first result is that the simple probability of getting +1 or -1 on both sides, they are 1/2, 50%. Looks totally random, independently of the orientation of the polarizers. Okay. But it's strongly correlated. What do I mean? I mean that if I get +1 on this side, I also get +1 on that side. I consider the situation when the two polarizers are along the same direction of analysis. If I have -1 on one side, I have -1 on the other side. And never +1, -1. Strong correlation. So I hope that you understand that this is really strange. You have here somebody tossing coin. Looks perfectly random. Somebody here tossing coin looks totally random. But when looking from the back, if you can see well enough, you observe that when there is tails here, there is tails here, and where is head here, it's head. And you say, where? There is a trick. This is what I call a tricky coin toss. And the role of physics is to understand tricky things, okay, to find the trick. The conviction of a physicist is that there is no magic in the world, there is a rational understanding of things. And so I want to understand the trick. I want to understand why, when I have +1 here, I have +1 there, although it looks totally random. What does it mean, understand? For me, and not all physicists would agree with me, for me, it means having an image in our ordinary space. And if I look at the efficient way of doing the calculation of the probability, in fact, I cannot make an image in our space. And the reason is that the calculation is done in an abstract mathematical space called the Hilbert space, which represents the two particles simultaneously. And so in that space, the mathematics are clear. But I don't know any way of plunging that abstract space in our ordinary space. I will show you later a way of doing it, but which is indirect. And so the problem is that I cannot identify individual properties for each photon, but I would like to have. I would like to say, okay, my source is here, photons are emitted, they travel. What happens? I want to understand. And I like this citation of a quantum theorist, Asher Perez, which says, quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. I want an image in my laboratory. In fact, there is an interpretation in my laboratory. And this was suggested by the famous paper of Einstein, Podolsky, Rosen in 1935. And the interpretation is the following. When the two photons are emitted, they have a common property. And this common property determines the result. Yes, it's simple. So for instance, from the beginning, they could be both photons could be polarized like that. Then you will have +1, +1. Next will be polarized like that. You will get -1, -1, okay? And so I want to insist that this image is rational, scientific. It's the same image that biologists or medical doctors developed long ago, before the time when you could see at the genetic code, when you had two twin brothers, same color of eyes, same color of hair, same pathology. They concluded that this was due to common set of chromosomes. It's exactly the idea. So you say there is a way of understanding this correlation is to admit that from the beginning, the two particles have a common property. Looks reasonable, but Bohr totally disagrees. Why? Because Bohr has the full conviction that you cannot complete quantum mechanics, and by introducing this quantity lambda, I complete quantum mechanics. Again, all the pairs as described by the same state vector, psi equal, bon. But here I say some pairs are like that, other pairs are like that, other pairs are like that. So I introduce a supplementary description underlying the standard quantum description. Einstein was happy with that because Einstein had a strong intuition that quantum mechanics should be completed, and in contrast, Bohr said, no way to complete it. So this is a debate. The debate between Einstein and Bohr was never settled between them. Einstein died in 1955, Bohr died in 1962. We have plenty of writings showing that they debated about that all along their lives without convincing each other. The reason is that the reasoning to try to convince each other was no longer a scientific reasoning. It was an epistemological discussion. It was an idea that you have about the world, the philosophy about the world. In 1927, at the famous Solvay discussion between Einstein and Bohr, Bohr came with an impeccable conclusion or discussion or reasoning, telling Einstein, look, Einstein, when you make your reasoning, you are wrong here. And at that point, Bohr was right. But in the 1935 about entanglement, Bohr did not come with an impeccable scientific discussion. He came with philosophical or epistemological argument like, you are not allowed to speak about something if you don't do the experiment. And in contrast, Einstein says, objects have a property independently of the fact that I measure this property or not. It was the root of the philosophical discussion, and it was never settled between them. But in 1964, John Bell made an unbelievable discovery. The discovery was that depending on the point of view that you take, the point of view of Bohr or the point of view of Einstein, then you can make different conclusions from a quantitative point of view. In other words, you don't predict the same results if you take the point of view of Einstein and if you take the point of view of Bohr. So there was a quantitative disagreement between the point of view, and you can settle the debate by an experiment. I don't know if there are other examples in the history of humanity where you can settle a philosophical debate by an experiment, but this is a case. There were 3 generations of experiments. The heroic pioneers between 72 and 76 with the name of John Clauser, who got the 2022 Nobel Prize. He found a result in agreement with quantum mechanics and in disagreement with Einstein. Well, there were some debates, but after a few experiments, the score was 3-1 in favor of quantum mechanics. Anyway, all these experiments were definitely different from the ideal schemes that I have shown to you, and this is why at the same moment in 74, I embarked into a new series of experiments in building a new experiment in order to realize it with schemes closer and closer to the ideal scheme that we have discussed. So this is John Clauser with his apparatus, and now the experiment that I did, and the result came in 81, 82. So the key of my experiment was a source of entangled photon, which was really complicated, 3-laser vacuum chamber, atoms in the vacuum chamber, flying freely, etc., etc. The result was a source of entangled photon much better than the previous one. And this is a key. In physics, if you have a good source, a lot of signal, then you can do more sophisticated experiment. And with this, I could do experiment that nobody had done before. The first one was this one, which really resembles, where is my pointer? It's here. It really resembles the schemes that I have shown you, because for the first time, I could have real polarizer, giving channel +1 and -1. Before, they did not have polarizer like that, so they had only the channel +1. They have to guess what is a -1. There is plenty of indirect reasoning. It were a nice experiment, convincing result, but plenty of intermediate hypotheses. Here, I could directly have the two polarizing beam splitter. For Jacques Lukasik, which is here, this was made for me by Philips in Eindhoven. And because it was too expensive for me to pay for it, they gave it to me freely. Okay. So I must be grateful to these people. Then, the final experiment, the one which granted me a Nobel Prize, the idea was the following. Bell had argued in his paper that to have the full conflict between Einstein's vision of the world and quantum mechanics, you should be able to change the orientation of the polarizer at the last moment, while the photons are in flight. I have no time to go into details of the reasoning. Maybe we have time later, but if you can change the orientation of the polarizers while the photons are in flight, you forbid any possibility of communication between the two ends of the experiment, unless this communication could be faster than light. And so by doing an experiment like that, the Einstein point of view is really totally put into action by the fact that, one, you think that the photons' properties are with supplementary parameters, so you have completed quantum mechanics, and moreover, you don't accept any communication faster than light. And this is which is at stake. This is what you are going to probe, to test. And the result was, sorry, Mr. Einstein, but you are wrong. Sorry, quantum mechanics survives the test, so something is wrong in your image of the world. Okay. To make a long story short, but it is important for application, there was a third generation of experiments. Once again, progress in the source. My source was much better than the one of Clauser, but they developed by the end of the century, they developed a new source of entangled photon, much more efficient than mine, in the following sense. In my source, photons were emitted in any direction in space. So I had to collect them with big lenses, and meaning beams which have a certain size, etc. In the new source, people exploit a phenomena which is nonlinear optical phenomena, and in such a phenomena, the photons are emitted along a well-defined direction. So well-defined that you can introduce a photon in optical fibers. And once you have introduced a photon in an optical fiber, you can go far away. So for instance, in this experiment that was done in '98, Zeilinger and his colleague Greg Weiss could have a 200-meter long optical fiber, which lets enough time to run a random number generator to choose randomly the orientation of the polarizer at the last moment. In my case, I was changing rapidly, but not randomly. Here, they do it randomly, which is a step further. It was '98. At the same year, Nicolas Gisin in Geneva did something which I liked very much. He introduced a two-photon in the commercial optical network of optical fibers, okay, in the telephonic network in Switzerland. So he introduces the two photons here in Geneva, Cornavin, and he makes the observation in two villages, Bellevue and Bernex, which are at kilometers from and he observes entanglement at kilometers. So really, this is due to the new source of entangled photon. Conclusion, the Einstein point of view has to be rejected, and I'm going to discuss that for a few minutes. The point of view of Einstein, we call it local realism, and I explain what it means. It means that Einstein tells us, if I have a system here, and when I do that, I think in space-time, that is in space and at a moment, okay? When I have a system here in a well-defined volume of space-time, in that volume of space-time, I have all the parameters which are necessary to know what will be the result of any measurement I will do on the system, and moreover, it allows me to predict the future evolution. And Einstein calls it the physical reality of the system which is here, okay? And this physical reality is local. It is in a certain volume in which the system is, okay? We have to reject this point of view after the results of these experiments. What can we conclude? Well, in fact, Einstein told us what you have to conclude. So probably you are surprised. You say Einstein did not believe in what he was saying. Of course he believed in what he was saying. He made the reasoning ad absurdum. He said, if I was not right, this is what you would have to swallow, and it is so unbelievable that obviously I am right, Einstein speaking, okay? But now we know that he is not right. So this is what we have to swallow. So these are the words written by Einstein. We have either to abandon the independence of the physical reality present in distant volumes. It means when I have two systems which are separated, I have a physical reality here, a physical reality there, and they are independent of each other. Well, we have to renounce that in a sense, and this is called quantum holism, meaning that the ensemble of the two is more than the sum of this and that. Or, say Einstein, you have to accept that the measurement on the first system affects, changes instantaneously the state of the other one, which is at a distance. This is called non-locality. In fact, the two points of view are not so different from each other, but anyway, it's good to present it like that. Well, first because Einstein presented it like that, but also because we have two series of applications which are based on one point of view or the other one. Quantum holism tells us in two entangled systems, I have more than in the sum of the two systems. That the idea is that you can put more information in an entangled system than in an ordinary classical system. So when you have only two entangled systems, the supplementary information is not that big. But if you have 3, it doubles. If you have 4, it doubles, etc., etc. And you have an exponential growth. And you all remember the story of the grain of corn, 1 grain of corn, 2 grain of corn, 4, 8, etc. And you know that after 64, you have an amount of corn which is unbelievable. Here, the same thing. If you have 100 entangled qubits, a qubit is a quantum bit. If you have 100 entangled qubits, the amount of information that you can put in them, we cannot even think of it. It's more than the number of atoms in the universe, etc., etc. It's unbelievable. That's the magic of exponential growth, okay? So the idea of the power of quantum computing is based on the fact that if you can entangle many, but many is not 1 billion, just 100 of perfect qubits, the amount of information that you can put into it is absolutely extraordinary. And so with this apparatus, you make a single transformation and you have a massive transformation of all this data. It's massive parallelism. That's the basic idea at the root of quantum computing. Quantum non-locality is at the root of several features which are in the framework of quantum communication. And I will just emphasize the fact that quantum non-locality allows me to make images which allow me to understand intuitively the power of these quantum information methods. Before doing it, I will make a plea for quantum non-locality. On this point, not physicists agree with me. In fact, you have to understand that facing the difficulty to understand quantum mechanics, there is a majority position which consists of saying, don't ask questions. You make a calculation, you compare the result of the calculation to the experiment, it agrees that's the end of it. That school is called by my friend Bill Phillips, Nobel Laureate in 1997. He calls that the school of shut up and calculate. Okay? Calculate and don't ask questions. Okay. I don't belong to that school. I like to have images. And for me, the only reasonable, between quotes, the only image I can have to describing, you remember what I told you, I want an image in our space. The only image that I have in our space is non-locality. And I'm going to show you a small reasoning based on a quantum calculation which gives an idea of what is quantum non-locality. I insist that this calculation is perfectly orthodox. I use only principles which are in our Bible. Many of us have that Bible. The Bible is a book of Claude Cohen-Tannoudji, Bernard Dieu, and Frank Laloué. I use only things in that book. This is the idea. The experiment, where is my pointer? It's disappeared? No, it's here. I assume that I first do a measurement here. Maybe this polarizer is a little closer to the source than the other one. And then I can get randomly result +1 or result -1. Result +1 corresponds to polarization X. If I have that, what do? I go to the Bible, and there is one principle, which is the principle of projection, projection postulate. Just after the measurement, I have a new quantum state, which is obtained by projecting the initial quantum state, which is here, onto the result that I have obtained. And the result of that projection is XX. So you know, before the experiment, I could not attribute any property to the two photons. I do the measurement, now I know that this one is X, and instantaneously, the other one is X. That's non-locality. So same for the O. If I find -1, it's Y, the other one is Y, etc. I do the reasoning, and I get the same results that I had with the compact calculation. Okay. So I have now an image in real space yielding the same result as the calculation in the abstract space. So I am happy because I have an image in our space. But of course, there is something special about that image, something that Einstein could not accept. Until the last moment, it can still be +1 or -1 on each side. But at the very last moment, the measurement is made. If I get +1 here, I get +1 here. And if I get -1 here, I get -1 here. This is non-locality. And non-locality allows me to have intuitive pictures, for instance, for quantum cryptography. Just this example of application of the notion of quantum non-locality. The problem, everybody understands it, you have two friends, Alice and Bob. I hope you recognize them, the nice Alice and the nice Bob, okay? They are friends, they want to communicate secretly. They don't want that the eavesdropper, the guy who listens, big ears, okay? An eavesdropper is a big ear. They don't want the eavesdropper to know their message. And there is a method which is proven absolutely safe. It's a mathematical theorem, nothing to do with quantum mechanics, okay? It's a mathematical theorem demonstrated by Bob Shannon, the founder of the theory of information, which is the following. If Alice and Bob have two identical series of numbers, randomly distributed, 0, 0, 1, 1, 0, 1, 0, and if they are the same, Alice uses the first encoding key, and Bob uses the same decoding key, and it's absolutely safe under one condition. The length of the key must be longer than the message. because if the key is shorter than the message, you use it several times, and the guy, the eavesdropper, these mathematicians are extremely smart, and they will notice a kind of periodicity, and they will be able to decipher it. So the problem boils down to distributing to Alice and Bob identical random series of numbers. And if you followed what I told you previously, you easily understand that the entangled photons are a good solution. So the idea is the following. I have a source of entangled photon, which is here. Now I've drawn a modern one, much better than mine, okay? It's simpler and efficient. You put it in optical fiber. And then Alice and Bob change the orientation of their polarizers. When the experiment is finished, they can communicate by open radio. It doesn't matter that Eve listened to that radio. And they, at the end, they conclude that for the first, the second, the fifth, the seventh occurrence, they are the same direction. So when they are the same direction, they know that the result have to be the same. Random, but the same. And so they take this number as a coding, decoding, and encoding and decoding key, okay? Why is it that the eavesdropper cannot make a copy of it? Because of non-locality. It is only at the very last moment that the decision is made to have +1 or -1. And so there is nothing to spy in between. And you are going to tell me, how do I know? I know because if there was something to spy in between, it would be supplementary parameters, and there would not be violation of Bell's inequalities. The violation of Bell's inequality shows that you cannot have something in between. It is only at the very last moment. Okay, there are plenty of other examples of that. So I must go to the end of this, but this I already explained you, so those who did not hear me, they can read now, okay? Something interesting, our Chinese friends have a satellite called Messius. On this satellite, they have installed a source of entangled photons. And they are able to observe entanglement as more than 1,000 kilometers, and they have done a demonstration of quantum cryptography at 1,200 kilometer distance. Since I am not late on my time, it's a moment to tell you that I think that there is a device which is still missing. Well, it is a good quantum memory. What would be a quantum memory? Quantum memory would be a system in which a photon, whatever its state, including the strange state that you have in a pair of entangled photons, you store the photon, and on demand, later, you push on a button and it's re-emitted. Let's suppose that you have a good quantum memory. You put it in the satellite. You send the first photon, you keep the second one in the satellite, in the memory, you let the satellite progress, and maybe when it is on the other side of the Earth, you send the second photon. And with this, you could distribute pairs of entangled photons anywhere on Earth. And I think that a good quantum memory is not so far from the possibility. There is no basic physics principle saying that you cannot have a good quantum memory, and so I encourage young people who want to work, they may be interested in working in a good quantum memory. Okay. It would be good also for quantum teleportation. This is another story. I have no time to speak about it. Okay. So, what is the second quantum revolution? The second quantum revolution is based first on entanglement. This you have understood. I have spoken of entanglement for more than 30 minutes. But there is another thing which was implicit, and now I want to emphasize it because it's crucial. Starting in 1970, physicists became able to observe, manipulate single quantum objects. This was a big surprise for many of them, because previous that time, most of the physicists thought that quantum mechanics was good for describing a large ensemble of quantum objects. For instance, many electrons in a piece of metal, or for instance, many photons in a beam of light. Okay? But starting in 1970, Mr. Demelt was able to trap a single electron in a electromagnetic trap, which is here. I hope you can see my pointer, yes. So here, he can trap the electron and observe it for weeks and manipulate it, change the orientation of the spin, etc. Don Eigler in IBM was able to manipulate single atoms on the surface of a crystal, etc. We were able, with Philippe Grangier and later Jean-François Roch, to produce single photon, observe single photon, etc. This is Serge Haroche trapping single radio frequency photon in a cavity, manipulating it and seeing it disappear and die progressively, etc. Last and not least, in Saclay, Daniel Estève and Michel Devoré could build a system based on superconducting devices which behave like a single quantum object, and there is a full activity on that. It's not yet completed, but if it succeeds, then you have the possibility to implement thousands, dozens of thousands, etc. of them. So these are called qubits, okay? The possibility to manipulate a single object and to identify two states on each of these objects means that you have qubits. This is as important as entanglement. So the second quantum revolution, remember, entanglement and single quantum objects. Quantum technologies. Can we go from concepts to applications? The answer is yes, at least there are plenty of proposals and first proof of principle. Quantum communication, I already mentioned it, it works. It's complicated, but it works. You need a dedicated device, not so dedicated, but okay, it works, it's difficult, but if you absolutely need it, you can have quantum cryptography. Quantum teleportation is transporting a quantum state from one point to another one. Why is it important? Suppose you have here a quantum computer. The output is a quantum state. If you make a measurement to read the quantum state, you destroy a part of the information. If you need that for the input of a second quantum computer, the best idea is to transfer it as a quantum state. This is quantum teleportation. So quantum teleportation is not Star Trek. It's not teleporting me or you or anybody. It's teleporting a quantum state. And for a physicist, teleporting a quantum state is just as surprising as transporting a big man like some of us. Okay. Quantum computing, big question. You have to distinguish imperfect and perfect quantum computer. Imperfect quantum computer do work. There are examples. For instance, I am proud that one of my former students, Anton at the Institut d'Optique, has an ensemble of 300 entangled qubits. They are not perfect, but they can anyway solve a problem which is a real problem. I mean a problem which was already in the books of physics called the Ising problem. It was well known that you cannot solve this problem by brute force for more than 50 particles. With this quantum simulator, he solved the problem for 300 particles. So this is an example of a quantum advantage, okay? And I insist, when you read a newspaper, quantum advantage, look at the problem they are solving. If it is a problem which has no interest, I don't call it quantum advantage. You need to have a problem which existed before you attack it. Okay, so with imperfect quantum computer, you can solve some problems. But the holy grail would be to have a perfect quantum computer, and perfect quantum computer means that you are able to do quantum error correction. Because in real world, nothing is perfect, it's well known, okay? And so what do you do when something is not perfect in information? You use redundancy. You encode the information in more than one bit. So in classical informatics, for instance, you encode on 3 bits rather than 1, and it's enough to have to fight errors. The problem with quantum bits is that to make error correction, you need many, many quantum bits to have only one logical qubit. For sure, if you have 1,000, you can make one logical qubit. But there is no reason that you cannot have less, but this is under research, okay? This is active research. And so, for the time being, we don't have yet an error-corrected quantum computer, but there is no reason why we could not have one. And I have a deep belief, based on my experience, which is that when something is not forbidden by the basic law of physics, sooner or later, the engineers succeed in doing it. I can cite you many examples, but now my time is flowing. Quantum metrology, it works. This is an apparatus developed by some of my former students, again, for measuring gravitation with a quantum phenomena. It's better than any classical measurement of gravitation. It works 24 hours a day, 7 days a week, on the slopes of volcanoes to see if by observing the fluctuation of gravitation, you can anticipate the volcanic eruption. So this would be a nice application. Okay, so we speak or we hear about quantum advantage. What would it be? Two possibilities. Having a computer able to do calculation that you cannot do with a classical computer. So I call it computing power. But the other face of the coin would be doing with your quantum computer calculations that you could do with a classical computer, but with much less electricity, much less energy. And as you know, this is a real issue. With AI, now big companies are having nuclear plants just for their computing centers, okay? So if you can do the similar calculation with less power, it's something which is very important, especially when you try to convince young people to work in the domain, because young people are especially obsessed by the problem of the planet, and if you tell them that by working on a quantum computer, they may save a lot of energy, you can convince the best of them to come and work with you. Okay, so nobody knows if it will work, when it will work, okay, but many believe in it. So here I cite state, okay, Europe, France, Région Île-de-France, but of course any country in the world has its quantum program. Big companies. I was recently in Korea and in Taiwan, and I observed that these big companies, Samsung, you have heard of Samsung, huh? Foxconn, you have heard of Foxconn. They have a department for quantum information, okay? Of course, all these one you know. Many startups. I must claim that I have a conflict of interest because I am one of the co-founders of Pascal, and I am in the scientific advisory board of Quandela, so you have to know that I am not fully objective when I speak about that, but well, I think I am first a scientist. Many other, and I forget many, this fascinating perspective, okay? And just to finish, it's finished. Okay, just to finish, it's finished. Thank you very much.
Thank you, Professor Aspect. I think I am entangled with your speech. I think we may have a lot of questions from the audience. So time for questions. Or you are all afraid
If you don't ask me question, I will be unhappy. Make me happy, like Schrödinger.
I can maybe start with one.
Yes,
I can maybe start with one. You showed a lot of examples about cryptography and quantum communication. Is there, from a sovereignty, geopolitical observation, a risk of split in the internet for those who will be first doing quantum communication networks?
Okay, I think that in fact, geopolitics is one of the main applications of quantum cryptography. And the reason is the following. You remember WikiLeaks. If secret diplomatic messages are released on a short term, it may be big scandal. After 50 years, it's no longer a scandal. But after a few years, it may be big scandals. And now let us think of the world where we are. There are big ears everywhere monitoring everything, including monitoring secret messages which are encoded with the traditional methods. But we have all reason to think that after 5 or 10 years, these secret messages can be decoded, because the security of cryptography at the moment is based on the hypothesis that your adversary is not more advanced than you either on a technical point of view, bigger computers, so you assume that basically his computers are about the same, or mathematically. There is no proof that there is not a theorem allowing you to factorize number faster than we think. We have example of that in the past. For instance, fast Fourier transform gave you a gain of 10 to the fifth on the time you need for calculating a Fourier transform. When I was a student, it had not yet been invented. It took 24 hours to calculate a Fourier transform. Now, you do it like that. You are going to tell me because computers are faster? A little bit. Mostly because of a mathematical theorem, fast Fourier transform. So we don't know. There may be a theorem for factoring big numbers. If these exist, your adversary can decipher your message. So in contrast, quantum cryptography is based on the hypothesis that quantum mechanics is right. Until this point, we have all reason to think that quantum mechanics is right. So I think that the long-term security is better guaranteed by quantum cryptography than by classical cryptography. So this is geopolitics, I think.
Thank you. Questions?
There is a young man in front.
There's a student over there.
A student wants to ask a question.
In well representation.
Alain cannot be more right because he was the professor that really was questioning me when I had to pass the test to enter at normal sup. I didn't remember at that time that he was the one making the selection.
So student one day, student forever.
Exactly. So you are right. Thank you for this amazing presentation. In terms of cryptography is a big topic, of course, with the virtualization of the world. Have you seen new type of connection between this representation of quantum phenomenon with biology, or in which sector you see a kind of similar metamorphosis, if I may say so, that could lead us to provide an orientation related to the imperfect aspect that can be a good solution to something which is anyway unknown.
Okay.
If I understood your remarks.
This is a big deal. There are often papers of people claiming entanglement in a biological phenomena, but usually it's wrong. They make a confusion between coherence, which is related to the first quantum revolution, and entanglement, and especially entanglement at a distance. Because entanglement at the scale of a molecule, yes, you have it all the time. You have several electrons in a molecule. Take the atom of the molecule of benzene, okay, something like that. Yes, you have a state which is like an entangled. But this is not what is surprising. What is surprising is what Einstein recognized, is the fact that entanglement can survive at a distance. This is the second quantum revolution. I don't know of any biological phenomena in which it happens, and the basic reason is the following. If you want to observe entanglement at a distance, you must preserve entanglement from decoherence. This is why photons are so good, because basically a photon is not affected by any perturbation, not affected by magnetic field, not affected by the only perturbation that you can have is fluctuation of the air where it propagates. But for instance, in my experiment, we don't even have evacuated pipes. We just have plastic pipes, the kind of plastic pipes you have in your house, okay? And it's enough to block any fluctuation of the atmosphere, and that's it. So this is why you can observe entanglement with photon at a distance. In a biological medium, it's hard for me to believe that you can have entanglement preserved. But again, I say it's hard for me to believe. I don't know that there is any general proof that it is not possible. So I think it's an interesting question, but the point is that often people publish papers in saying we have entanglement. No, they have observed quantum coherence, which is the first quantum revolution, which is already very interesting, but it is well known that in chemistry, you need to have that to understand many chemical phenomena.
And can I ask, just to rebound on Bernard's question, am I wrong in understanding that Roger Penrose, another Nobel Prize, has proposed some sort of correlation between consciousness and entanglement?
Well, this is extreme. What he proposed, which is not as extreme, is we have a big equation, fundamental equation, which is the following. Why don't we see a Schrödinger cat both dead and alive? And the standard answer is, past a certain scale, a certain level, there is the quantum coherence is washed out by decoherence. But these just words. We don't have any practical way of thinking where is the barrier between 3 or 10 or 100 entangled objects, and then 10 to the 23rd when you are at our scale. And so Roger Penrose has an hypothesis which is interesting, I think, which is that we don't know yet how to quantize gravitation. And we have good reason to think that when we quantize gravitation, as for any quantized phenomena, there are random fluctuations. And maybe these as a random fluctuation would provoke the decoherence at a certain size of an object. This, I think, an interesting hypothesis. Now, the role of the mind, personally, I don't swallow that. I am just like Einstein. You know, I am an Einsteinian, although I proved that in a sense he is not right. Einstein once asked one of his colleagues, do you really think that the moon is not here if I do not look at it? So I think that we don't need to have a human mind to observe phenomena. So I would not follow Roger Penrose on that, but I would follow him on the first hypothesis, which is gravity. Let us try to interpret decoherence that would be produced by quantizing gravitation.
Very clear. We had a question over there.
Ah, voilà, maintenant il y a des questions. Over there?
Yeah.
Allez-y, allez-y.
Allez-y.
Okay, thank you. Well, thanks for a great, inspiring presentation. I'm more on the biomedical side, thus my question will be very naive.
Excellent.
There is a lot of interest those days in medicine, for example, in programmable intelligent matter. I'm not talking about interfering with biological processes, but injecting in the body nano devices in the form of nanorobots or nanoformulations, carrying drugs or whatever. And could we think of using this quantum particle entanglement to manipulate with some external, I would say, manipulation, in fact, or interferences, those objects to pilot them in the body?
Okay, well, you can dream of it, and I'm going to give an answer which is somewhat on the side, but which, in my opinion, is related to your question. One of the interesting use cases of the quantum simulators, the imperfect quantum computer, is to try to understand the shape of big molecules. So I know that you have classical computer for doing it, but it seems that it is a privileged application for quantum computer to understand how proteins fold, to understand, for instance, there is a paper published by the people of Pascal in connection with people who know application in biology and pharmaceutical applications, which is understanding in one of these molecules where the molecule of water go, you know, inside the molecule, etc. So when you want to know the behavior of this quite complex microscopic, but anyway, big quantum objects, then the quantum computer can be useful. It's not an exact answer to your question, but I think that there is some relation.
I think there is a clear application of quantum informatics to this part. I mean, developing drugs, for example, interacting with a target, with a protein. Those days we think in terms of perfect complementarity in the three-dimensional shapes. You know, that's the key and unlock complementarity. But now with quantum chemistry, in fact, we can think of know the position of the electrons and the
exactly.
And that's
this
really
is a use case for imperfect quantum computers. That is to say, the kind of quantum computer that we have already. Okay. So let us cross our fingers for people like me who are on this side.
very naive and basic question, which is, what is the connection between QC and AI? In both directions, could AI facilitate the development of QC, and to what extent does QC implement more efficiently AI than classical computing?
Yes, it's the second. First, I am not an expert, but I know an answer to the second part of the question. Let's suppose that you want to develop AI in a subject in which you don't have many data. You need many data in order to have, the AI developing. It's possible in some cases to use a quantum computer to generate data which are reasonable, which are plausible. And so this would allow AI to understand about that case with data generated by quantum computer. This is what I have heard from people who are more knowledgeable than me, but it seems to me convincing.
Thank you.
A last one.
Over there, a woman. No? Oui.
Thank you so much for this very inspiring talk. As a young researcher myself, I sometimes feel like I'm a bystander with the quantum revolution because I don't directly work in this field. So my question is, how can we contribute to the research effort even though we come from different fields?
I think that at the moment, it's probably by getting enough information about a quantum computer to find use cases. Nowadays, we really miss a lot of use cases. What I mean is that if tomorrow morning, it will not be tomorrow, but maybe 2 years from now, or maybe a little more, if we have a real, good, perfect, error-corrected, fault-tolerant quantum computer, and we give it to people, they know some applications, but there is not a systematic way of knowing how to solve a problem with such a computer, which means that we need good mathematicians to improve on what I say, but we also need people to say, hey, in my domain, don't you think that you could use a quantum computer for doing this and that? So you should go and talk to people of Pascal, for instance, they demand these kind of things, but I think in any startup in quantum computer, they want to hear about possibility of use cases.
Thank you so much.
Thank you. We're running out of time, so a very last short question. Very short. Mike.
Speak, you will have a microphone.
Thank you very much for your explanations. You quickly mentioned the idea of hidden variables. Can you please explain more how they interfere, this variable, with
These are the lambda.
Yes.
If you want to make reasonable the idea of correlation at a distance, the most natural idea is to say there is a supplementary parameter, hidden variable, for understanding this correlation. But the result of the experiment is that it does not work. It does not work. You cannot think that the correlation are due to a property from the beginning. And my experiment, the last one, the one which led me to go to Stockholm, receive the medal, etc., in my experiment, because I changed the orientation of the polarizer last time, I demonstrate that there is no hidden variable. It is at the last moment that it is decided that it is +1 or -1, and then instantaneously the other one is +1 or -1. So hidden variable was a very nice idea. Einstein loved it. It does not work, period.